Okay, so last time we were talking about timers and counters, and in particular we were discussing the applications of timers and counters. Um, we said we are concerned with 4 different applications for timers and counters, which is the measurement of timing events, the count of external occurrences, and we stopped over here where we try to generate timing signals and to generate a pulse width modulated signal. Now, using the output compare for generating signals to interface external devices. Now, to generate the signal, one must compute the time required between the rising, fall, and the rising and falling edges. Suppose that the external device requires a pulse of 2 milliseconds wide to be activated. Now, to generate the desired pulse, one must first program the logic state of the particular pin to be low and set the time value using a specific register with respect to the contents of the free running counter. At the clock cycle, the special register contents are compared with the contents of the free running counter, and when the counter matches, the program logic state appears on the designated hardware pin. Yani, basically what we try to do here is okay, let me okay, so assume that you want to generate a pulse that is 2 millisecond wide. Now, the idea is your timer and counter may be running a higher frequency and running a clock pulses of a frequency, or your microcontroller is running at a frequency which is giving you a timing period for each pulse of around 500 micro or 5 microseconds. Let's say not 500, let's say 100 microseconds. Okay, your time here is 100 microseconds. Now, the problem with the 100 microsecond, if you try to apply it to a microcontroller, the microcontroller usually will not respond to this input. Yani, if you want to change the value very fast at 100 microsecond will not appear on the microcontroller. So usually we want the output pulse to be wider. Now, in order to do this, we need to know what is the time between the rising edge and the falling edge over here. Now, once we have the rising edge, we start our timer. So over here, we will start our timer. Now, the timer will stop over here. Here, we need to stop the timer. And on the output pin, here we go for the rising edge. And once we stop the timer, we go for the rising edge. Now, the idea is, how many pulses do we need? Okay, how many pulses do we need? To calculate the number of pulses, we need to say that each pulse is 100 microsecond and we have 2 milliseconds. So the 2 milliseconds is 2000 microseconds divided by 100 microseconds. So the microseconds with the microseconds will go, the 2 zeros with the 2 zeros will go. So we end up with 20 counts. So I will put in my OCR register 20. I will start my timer over here, and once my I will start my timer over here and put the pin output to high. Okay, I will put the pin output to high. I will continue counting. Once the compare match, the CTC happens, and I get a compare match of 20, so I'm counting to 20. Okay, so I will count to 20. So once my count reaches to 20, I will take the pin, my output pin, low, and this way I guarantee that I got the 2 millisecond time period for my signal. This way I will guarantee that I got the 2 millisecond time period for the signal. So this is basically how it is done as an application. Remember, once more, um, your microcontroller will output signals at very fast changing rate. Sometimes you want to capture that changing rate. Okay, sometimes you want to capture that changing rate. If you want to do this connection using a normal microcontroller, then you either take the output into a delay, and this again will waste the time of the microcontroller, or you need to somehow capture this event. The capturing of the event is quite important because microcontrollers, they run at very high speed, and it's somehow difficult to capture these signals. Now, again, this is an option for us to capture an event and produce an output signal. So once the rising edge is generated, in our example we saw it, the program must reconfigure the event to be a falling edge, low state logic, and change the contents of the special register to be compared with the free running counter. For the particular example, let's assume that the main clock is running 2 megahertz. So our main clock, our microcontroller, is running 2 megahertz frequency. The free running counter is a 16-bit counter. The name of the special register of the 16-bit register where we can put the appropriate output values is the output timer register. Okay, to generate the desired pulse, remember we want to generate a 2 millisecond pulse. We want to generate a 2 millisecond pulse using 2 megahertz frequency, 16-bit timer counter. So if we do the calculation, okay, if we do the calculation, what we want to do is, yes.
Sir, can you record?
It is recorded, don't worry. It is recorded. I'm recording it from my computer. I'm recording everything on my computer. Once I finish, I will upload it to SULMS. It will be more clearer and easier for you. Okay? So we want to generate a 2 millisecond signal using 2 megahertz clock or 2 megahertz microcontroller clock, and using a 16-bit timer counter. Now, we need to know how many counts we need to get 2 milliseconds out of the 2 megahertz. So first of all, the time period for each pulse is equal to 1 over 2 megahertz. 1 over 2 megahertz in microseconds, 1 over 2 is 0.5 microseconds. Next, we need to know how many pulses we need to get, or we need to generate 2 milliseconds. So the number of counts will equal to 2 milliseconds is 2000 seconds divided by 2000 microseconds divided by 0.5 microseconds. Again, microseconds with microseconds will go. 2.2 will give you 4000 counts. 2000 divided by 0.5, this will give you 2000 counts. So the contents of the register, the output compare register, will have the value of 4000 counts. Now, you cannot do this using an 8-bit counter. That's why we used a 16-bit counter. You cannot do this using an 8-bit counter. That's why, okay, you cannot do this by using an 8-bit counter. ليش؟ لأنه ال 8-bit counter will count up to 255. The 16-bit counter will count up to 65,000. Okay? Sometimes you need to use the 16-bit counter in order to get these results. This is also explained over here. Now, to generate the desired pulse, we can put 000 to the first output of the timer register. After the rising edge has been generated, we need to change the program event to a falling edge and put the value of 0FA0 اللي هو 4000 decimal. Okay, 4000 decimal, if you convert it to hexadecimal, it will be FA0 in decimal to the output timer register. As the case of the output timer module, we can output the timer system using interrupts to generate the desired signals as well. هذا the part of the interrupts I will be discussing inshallah in the next module. Okay, in the next module we will be discussing the interrupt systems and how to generate the how to use the interrupt systems along with the timer and counter systems. Now the next signal that we want to generate is the pulse width modulated signal. Now it is easy to generate a signal using the normal OCR. We saw that in the lab. We generated a signal using the phase correct pulse width modulation. So here we are explaining this in more details. So the task necessary is again to turn on the timer system configuring a physical port. Remember, I can generate a signal very easily. I can here come and say I want to generate a pulse width modulated signal. I will just say let's say DDR A is equal to 0xFF, and then I will say while 1, and I will open a bracket. I will say port A is equal to 0x00. Then I will put delay underscore milliseconds underscore, let's say 500, and then I will say port should be in capital. Port A is equal to 0xFF. Then I will say delay underscore milliseconds underscore 1500, and then I will close my bracket. Now this will generate a signal that is low. Okay, the signal is low for 500 milliseconds. Sorry, this is microseconds. 500 milliseconds, and it will be high for 1500 milliseconds. Now, what is the duty cycle over here? What is the duty cycle for this signal? It is 1500 divided by 2000, which is 75%. Okay, the duty cycle is 75%. Now I can do that, and you can do that. I know you can do it because you have done it before, okay, during the lab. But this is not what we are trying to learn. In this method, this delay is useless. You cannot use this delay. Yani over here, I'm telling the computer, I'm telling the computer over here, I'm telling the computer to do what? I'm telling the computer, you need to stop whatever you are doing for 1.5 seconds. 1.5 millisecond is 1.5 seconds, and just delay, freeze, which is not right. So, in order to do the same thing using the timers and counters, we need to program the timer and counter and then see how it operates. So the first task necessary again to turn the timer system configuring the physical port, and a program event is using the rising edge. As part of the initialization process, we need to put zeros in the timer registers we discussed in the previous sections. Once the rising edge is generated, the program then needs to modify the event falling edge and change the contents of the output timer register to a value proportional to the duty cycle. Now, for example, if we start with 25% duty cycle, we need to input 4000 to the register, provided that we are using 16-bit register free running timer counter. Once the falling edge is generated, the now timer needs to go back and change the event to a rising edge, and the contents of the output timer counter is back to zeros. طبعا ليش we put 4000? Why did we put 4000? Because basically 4000 is 1 over 4 of the 16,000 or FFFF for the register. Okay, so what I'm trying to tell you here, if I am to generate 25% duty cycle and my timer counter is running 16-bit, then what will happen is 16-bit will be counting from 0 up to 2 to the power 16 minus 1, which is FFFF 1 over 4 or 25% of this count اللي هو 4000 hexadecimal. Okay, so you will put the output compare register to 4000 value. But this is based on the frequency of the system. What if I want to change the frequency of the system? يعني assume that I want to generate a signal. Okay, assume that I want كيف كانت control Z. Assume that I want to generate a signal, okay, and the signal has a frequency, let's say 500 kilohertz, and a duty cycle of 40%. So I will have two tasks. First, I need to generate the signal. Then I need to set the duty cycle. Two separate tasks. Okay, you have two separate tasks. The first task is to generate the signal. The second task is to generate the duty cycle. This is what we are going to see over here. Now, if we want to continue to generate 25% duty cycle signal, then we must repeat the process indefinitely. Note that the rising, we are using the timing of the free running timing counter, which is counts from 000 la FFF. The FFF is 2 to the power, this is 2 to the power 16 minus 1. Now suppose that we want to increase the duty cycle to 50% over 1 second, that the clock is running 2 megahertz. Okay? In order to do that, this means that the free running counter counts from 000 to FFF every 32.758 milliseconds. And the free running counter will count from 000 to F every for approximately 30.51 times. That is, we need to increase the pulse width from 4000 to 8000 in approximately 30 turns, or approximately clock 456 clock cycles. Now, what does this mean? It means we want to generate, okay, it means we want to generate a signal. Okay, so we want to generate a signal which has a duty cycle. Our duty cycle is equal to 50%, and the time is 1 second. Our clock, the microcontroller clock, the microcontroller is running 2 megahertz, and we are using 16-bit timer, and that's it. Okay, let's go here. So we need to know how many times do we want to do the timer counter. So in order to do that, first of all, how many counts do we need to get 1 second out of the 2 megahertz? Okay, so my timer counter will be counting 2 to the power 16 minus 1. Okay, 2 to the power 16 minus 1 on a frequency of 2 megahertz. So how long does it take to count from 0 to 2 to the power 16 minus 1? So in order to do that, we need to do 2 to the power 16 minus 1 multiplied by 1 over 2 megahertz. So this will be, my calculator is not here, so we do it together on the computer. So I will use the scientific calculator, and over here I will have I will have like this. 2 to the power 16 is equal to, 2 to the power 16 is equal to minus 1 is equal to, this is 2 to the power 16 minus 1, multiplied by 0.5 microseconds, okay, multiplied by 0.5 microseconds, which is, okay, I'm not used to using this calculator, 65535, okay, 65535 multiplied by 0.5 will give you 32. Okay, this is 32,767 microseconds. Remove so this will give you 32, 767 microseconds, or 32.767 milliseconds. So each time your microcontroller counts from 0 up to 65535 اللي هو 2 to the power 16 minus 1, it takes 32 milliseconds. So how many times do I need to count to 65,535 in order to reach 1 second? So in order to do that, I need to say 1 second over 767 will equal to 1 divided by 32.767. Okay, this one multiply by 1000, it will be equal to 30.5 times. So I need my timer and counter to count from 0 to 65,000. Okay, I need my timer and counter to count from 0 to 65,535. Okay, around 30 times 0.5 in order to get the 1 second period. So I need to count 30 times. طيب, my original signal, I want to generate a 50% pulse width modulated signal. So this means my timer and counter will start from 0. Once I count the first, once I finish counting the 65,000 for the first time, I will have the count 1, 2, up to 30. In the middle, once I reach 15, my signal will change from 0 to 1. Okay, so I will count from 0 to 30. If from 0 to 30, it will give me the full 1 second. From 0 to 30, it will give me the full 1 second. Half of that time, I will be doing it low, and the other half, I will be doing it high. This is how I will generate the signal. And this is what exactly is written over here, but in less details. So you can see here that we need to increase the pulse width from 4,000 to 8,000 in approximately 30 turns, or approximately clock counts every turn in order to get the value. So we got the value of 30 turns, and we increased the pulse width in order to get the 50% duty cycle. Now, this is all good, this is all clear, hopefully, but how do we use this information to control the motors? How do we use this information? Okay, how do we use this information to read the, how do you use this information to control the DC motors? Now, the DC motor operation is a little bit more different. We have, remember, we have two motors we are talking about over here. We have the DC motor and we have the servo motor. In the case of the DC motor, it's quite simple because we generate a signal and we just apply a pulse width modulated signal. We don't care much about the frequency in DC motor. In the servo motor, it's mostly about the frequency. In the servo motor, it is mostly about the frequency, and it's very important to include the value of the frequency. So a DC motor has a positive and negative terminals. When a DC power supply of suitable current rating is applied to the motor, it will rotate. If the polarity of the supply is switched to the reference terminals, the motor will rotate in the opposite direction. The speed of the motor is roughly proportional to the applied voltage around it, and as you know, we use the H bridge for that. So this is your H bridge, this is your two DC motors, and this is the L293D H bridge, which you already know because we have used it previously. This is a simple connection, and as you can see here, the enable is connected to VCC. Once the enable is connected to VCC, this means that the motor will be running at full speed all the time. What we want to do is to remove this value and connect it to another output. Now, in order to get a pulse width modulated from the AVR, we need to use the timer counter module of the AVR. This module can be used in several modes to generate different pulse width modulated signal, as you know. Here we shall be explaining how to use the timer counter in the phase correct pulse width modulation of the 80 mega 32 in timer counter 0. So the first correct pulse width modulation, the counter counts repeatedly from 0 to the maximum, which is FF, and back from the maximum to 0. The output pin, which is output compare 0, as you remember over here, it was, I always lose it, this one, output compare 0, this one will be connected over here to the enable. The output compare 0 will have the value and is cleared when it reaches the compare value, while the upcoming, the upcounting and the set continues to reach the same value and counting down. This compare value is set by a software in a register called output compare register 0. Okay, output compare register 0, while the value of the counter itself is contained in the timer counter 0. When the value of the timer counter 0 reaches the OCR, it's called the compare match, and the timing diagram explains what happens. So this is what happens. When we reach the OCR 0, we change the output and so on. This is what we used previously in our lab, and it's the same diagram that we used earlier. Now, let me fix this one. Why it's like this? Okay. You can also invert the output by changing the values of COM1 and COM0 in the timer control register. In that case, the output is set with the compare and reset with the going down of the signal. اللي هو بيعطيك will give you the opposite. Now, the duty cycle of the correct pulse width modulation signal can be calculated. Duty cycle is equal to 255 minus the OCR 0 multiplied by 2 over 255 multiplied by 2. طبعا the multiplication of 2 over here, because in the phase correct it is taking twice the normal time of the fast pulse width modulation signal. Now, in this lecture we will use 3 different duty cycles to change the compare output register based on the push buttons, which we did in the lab, so I removed it from here. So let's get configuring the pulse width modulation signal in 2 steps for the TC, timer counter control register, and the OCR register. Now for timer 0 and the ATmega 8515, this is the timing signal, this is our output counter, this is the clock, and these are the timer, and this is the output compare register we are talking about. So the configuration, the one similar to the one used in the lab. Okay, this is the same one used in the lab. Okay, so the configuration of the timer counter control register A and the timer counter control register B, because it is different from one microcontroller to other. Remember, with whatever microcontroller you use, you should have the data sheet for it. So the sets of bits for the wave generation modes is 0, 1 respectively to enable the phase correct. The COM0A and COM0A1 are 0, 0, 1 respectively, so we will have pulse width modulated signal inverted. And the clock select 00, 01 and 02 is 101 respectively, which is this one. This will enable 1024 division of the clock time cycle. Okay, so we have the wave generation modes, as you can see here. Okay, this is the same information for this table, and then we have the descriptions for the COM values. Then we have the code select or clock select values. This is, by the way, this is the same as the one we did earlier in the previous class. Okay, these are similar to ones we did in the previous class. So then we will talk about the servo motors. I will stop here because servo motors is more, and I need to discuss in details how it is done. It's more about equations, but I will stop here. And this is the only part included in the test on Tuesday. Servo motors are not included. It's just DC motors and what we have discussed in the previous classes. Do you have any questions on this part? If you have any questions, please, I'm happy to answer you. I will upload the lecture after just 20 minutes. I will upload it to SULMS. Okay, I will upload the lecture on SULMS after just 20 minutes. Do you have any questions? Naam.
Can you please tell me how to study this part, like revision for the exam? Because I don't know exactly how what to study?
You in this part, you need to study. You need to know how to configure your timer counter for any frequency and duty cycle. At least not for any frequency, for any duty cycle. لأنه the frequency is a little bit more different. لأنه the frequency you need to the only way to configure the frequency, by the way, at this time is to use the dividers, okay? Because up till now, what I have assumed is my timer and counter will always count from 0 to max. We did not add a top, because if I add a top, which we are going to talk about later on, my timer and counter will be having different frequencies. But for now, the only way to control the frequency is by simply controlling the dividend values over here. It's either the clock divided by 8, 64, 1026, or 256, or 1024. So you need to understand how to do this part. You need to understand the timers and counters. Usually when I ask about timers and counters, I will ask you to write a program for a specific timer and counter for a specific application with a duty cycle and frequency. So you need to know how to do that.
But doctor, from where do we get the tutorial for this? I mean, for writing the codes.
From the lab. There is no tutorial. It's just from the lab. The things that we did in the lab. That's why there is no tutorials, because whatever we do in the lab.
Yeah, doctor, but we did only one part. You did the last lab. You only talked about the counter.
Yeah, the counter. This is the only part included in the test. Nothing more is included.
But you didn't explain like all the part about the counters. Good, I didn't understand it.
I explained it, but you did not understand it. It's not I did not
yeah,
explain it. I explained
the
it.
The program was crashing a lot for you.
Yeah, and it was recorded for you. The explaining for the program is over here, Mahmoud. The explaining of the program is just over here. This is the same program I used. This is the timer counter control register 0. You see it? Here is the value of the timer counter control register 0, which we used in the lab. This is the value of the timer counter control register 0. What we did in the lab is put the timer counter control register 0 to a value, and we just changed the value of the OCR register. This is the two things. The lab was 3 lines. Okay? The lab was 3 lines of code. The timer counter control register 0, and the timer control register 0, and the mask register, we put it all to zeros. 3 lines of code.
Okay, doctor, I understood.
Okay. Any other questions?
دكتور
نعم.
بالنسبة للإجابة في الاختبار هل ممكن نكتب في الوورد بعدين نعملها نسخ؟
No. It's not because I don't want, because the paste option is not allowed in Moodle, in SULMS. When we start a test, if you try to right click, it will tell you this function is not allowed. Pasting is not allowed. Remember, pasting is not allowed. You need to type everything by yourself. المشكلة مش من عندي، المشكلة في الموديل نفسه. Moodle will not allow you to paste any code, to paste any sentence. You need to type everything by yourself.
دكتور يعني بكفي الوقت ولا بيستدعي النظر؟
والله بكفي، أنت وسرعتك. I will not change the exam so that it will fit the slowest typers. It's moderate for all. And you see here, the typing is not much. When we talk about typing, it's typing a program. The lines are not big, and it's not like typing a paragraph. I'm just asking you to type the lines in the right way.
Doctor, Are you going to upload a mock test?
It's already uploaded. It is already on SULMS. Any other questions? Okay, if no questions, I will stop here and I will see you inshallah again on tomorrow. Tomorrow we have a class, and on Tuesday we have our test and we have our lab. See you all.